What's going on, guys? My name is Matt and this is my first attempt at making a handheld gaming PC. This system is able to play pretty much any game at 720p, with most AAA games sitting between 40 and 50 FPS on average. For example, here it is playing Borderlands 3, one of the most intensive AAA games I play on a regular basis. I made this with mostly off-the-shelf parts. I did have to make a fair number of modifications and I'll be showing you the full process in today's video. Now, this isn't the most powerful system ever, but it does have a Ryzen 7 APU, plenty of RAM, and an NVMe SSD. One other nice thing is that it has a multi-touch Full HD panel that makes navigating Windows 10 a breeze. It's definitely rough around the edges and it's not 100% done, but I'm at a place where I'm ready to show it off and see what everyone thinks. Now, I started this project many months ago, but my work on it has been very sporadic because of my need to order parts from China and wait for shipping. Not many people have attempted something like this, and I'm not that well versed in circuits and electronics, so trying to make a handheld gaming PC seemed like a monumental task. Originally, I wanted to source a single board computer like this one, along with some 18650 batteries to make things as compact as possible, but finding a small single board computer with the size and features I needed was next to impossible. Going this route would also mean I'd need to design and implement my own battery and power management system, which at this point is too far over my head, but I'm definitely going to go that route the next time I try to build a handheld gaming PC. Because of all this, I decided the best thing to do was to source a laptop motherboard along with its original battery. This would take all the guesswork out of charging and power delivery. I did a ton of research and looking before I eventually stumbled upon this board right here. This is a motherboard for an HP Envy X360 laptop. Though this model was released a number of years ago, this board was the perfect fit for this project for a number of reasons. First and foremost, it was relatively inexpensive. I purchased it from Impact Computers for about $54 plus around $10 for tax and shipping. With this being a relatively inexpensive board, it took some of the stress off of me because I knew getting a replacement wouldn't break the bank. Unfortunately, this board has now jumped up to nearly $200. On it is a Ryzen 7 2700U processor with integrated Vega 10 graphics, 2 DIMM slots, an NVMe slot, and all of the I/O and power delivery components. This was definitely bigger than what I originally imagined the single board computer would be, but again, it fit the bill, so I proceeded with the project. To cool the 2700U, I need to purchase the original cooler for this laptop, which I got for around 20 bucks. The one big problem with this cooler is the fact the fan assembly is meant to sit to the side of the motherboard, but I needed the entire cooler to fit within the footprint of the board itself. This meant a few different modifications needed to be made. First, I had to relocate the cold plate that mounts to the motherboard. Doing this was surprisingly simple. I first hung the cold plate off of a table like this and used a heat gun to melt the solder which separated the two pieces. I could then figure out where along the heat pipe and in what orientation to reattach this. Now, to reattach this, all I need was this stuff called solder paste, which is small pieces of solder suspended in flux, and different pastes melt at different temperatures. So the flux suspends the solder where you want it, and applying heat removes the flux and leaves the solder in place to connect the two pieces of metal. Once I had the location decided, I applied some solder paste, clamped the piece together, and began applying heat. Now, I almost went too far, and you can see the heat pipe expand and almost burst from the amount of heat I was applying, but luckily everything's fine, and now I know what not to do for future projects. With that done, the cooler successfully fit within the footprint of the motherboard. The only problem is the short fan connector didn't reach the fan header because of the relocation, so I had to snip, solder, and heat shrink extensions onto the connector so I could plug it into the fan header on the motherboard. With the main board and cooler figured out, I wanted to decide on the other large components before figuring out an enclosure. For the battery, I decided to go with the standard battery that would have come with the board in the HP Envy X360. Again, going with laptop parts meant power delivery, charging, and battery monitoring were all already controlled by the laptop mainboard. This battery is a 52 watt-hour OEM HP battery which is meant to connect directly to the motherboard, but because space was a big issue, I had to figure out a way to mount the battery away from the board and extend the connection, which I'll get into later. For the display, I originally wanted to use this extremely thin 9-inch LCD, which on paper should have worked, but after trying it out, I was not able to make it work. There were plenty of displays that were compatible with the eDisplayPort standard this laptop used, but the problem was all of them were over 11 inches, and 9 inches was the max I wanted to go for this project. Because of all this, I had to go for a much less elegant solution of using a 9-inch USB powered display. This required a USB and HDMI connection, which was disappointing because a display connected directly to the board would have only required this small cable. But the one bright side is while the display is very bulky, it does have multi-touch support where the original LCD did not. Now, because this was a handheld, it needed a built-in controller. I could have gone the route of sourcing all the necessary components and use an Arduino to control them like this guy did, but I decided to try and adapt an existing controller to work with my system. Bluetooth Joy-Cons like these could have worked, but I didn't want to have to deal with connecting them wirelessly or having to worry about charging them. Because of this, I wanted to go with a direct wired USB controller. After doing some brainstorming, I thought using one of those retractable phone controllers would work, but after doing even more digging, I found this, a wired switch controller dock. This was perfect as it had two separate PCBs with ribbon cables running between them and a single USB connection. With the controller, screen, battery, and mainboard in hand, I could begin figuring out how to put them together. In an ideal world, I would have modeled and 3D printed an enclosure, but I have not yet taken the time to learn 3D modeling, so I had to get a little creative. What I decided to do was buy these sheets of thin Kydex plastic. This is very durable plastic that, while flexible on its own, was plenty rigid for this project once components were mounted to it. I initially measured out the sizes I needed and ran a razor along a straight edge to cut the pieces, and this worked decently well. With this being said, I decided to try cutting these on my table saw, which worked even better. The one problem I ran into was the fact these 1 foot by 1 foot sheets weren't actually square, which was a pain trying to figure out which edges to slide along the fence to make sure the final pieces were as square as possible. I used these pieces to mount components to and stacked one on top of another. These layers were connected with various standoffs and screws, which allowed for variable spacing between layers. Doing this method definitely made the end product look pretty thick, but it worked out, and I'm decently happy with how this project is coming along thus far. This main centerpiece has the motherboard mounted on one side, the battery on the other, and the controller pieces on each end. For the controller, what I did was disassemble it, cut it in half, then cut each side until it was down to pieces like this. And just an FYI, throughout this entire process, I was testing things to make sure they were working as intended, because there were so many small details to this that one minor mess up could be a major detriment to this project as a whole. These controller ends were just attached with nuts and bolts. For the back panel, I simply took a piece of plastic and drilled a number of holes to act as an intake for the fan. For the top panel, I removed the back panel and speakers from the display and used the back panel holes to mount the display to it. With everything in its place, it was now time to figure out how I was going to connect everything. For the controller, I simply shortened a female USB-C to USB-A cable and plugged it into the breakout USB board like this. This plugs into the controller input board, which is double-sided tape on top of the main board. This isn't the most elegant solution, but it got the job done. For the display, I need to have a USB connection for power and touch input, and needed an HDMI connection for the display signal. After doing some research, I found these neat ribbon cables on Amazon. You can get them for USB and HDMI with various sized components and various orientations. To make the final product look a little bit nicer, I took the display's input board and mounted it further back into the display body so cables could be routed through the plastic backplate. The HDMI runs to the HDMI output on the board using a right angle connector, keeping things low profile. For the USB, I had planned on using this USB-C ribbon cable with a right angle connector, which fit perfectly here, but disappointingly this didn't work. I'm sure this has to do with the various differences in USB-C cables and standards, but unfortunately this cable just wasn't compatible. Because of this, I had to use a USB-C to USB-A cable which sticks out like a sore thumb. I'm trying to figure out a better solution for this, so if you have any suggestions, let me know what they are in the comment section below. For the power input, I simply mounted it so it was facing the bottom of the device. Unfortunately, I still haven't got battery power working yet. I purchased these connectors off of AliExpress and soldered wires to them to create a battery extension cable. Only problem is I initially mixed up two of the pins and think this may have damaged something. I'm hoping it's the battery itself and not the power interface on the motherboard, but this is something I'm going to be figuring out soon. And yes, I know a handheld doesn't have much of a point if it requires external power, but I'm sure I'll have this problem fixed within the next few weeks. So for now, the only way to play is plugged in. So as you can see, there were a fair bit of trials and tribulations to get to this point, but it's not done yet, and I will hopefully make a follow-up video when it's all finished. So now that you have an understanding of how I put this together, let's dig a bit deeper into the specs and performance of the system. So like I said before, at the heart of the system is the AMD Ryzen 7 2700U. This is a 4-core, 8-thread CPU with integrated Vega 10 graphics. This has a base clock of 2.2 GHz with a boost clock of 3.8, and I will be getting into real-world temps and clock speeds during the performance section. This has a manufacturer configurable TDP of 12 to 25 watts, making it pretty power efficient. Now don't let the name fool you, this is a 14nm Zen 1 processor and is not a 12nm Zen Plus, which isn't the end of the world but is worth mentioning. The board thankfully has dual SODIMM RAM slots, meaning dual channel operation is possible, but the max supported memory speed is 2400 MHz, with no option for XMP profiles or overclocking in the BIOS. This is unfortunate because of how heavily Ryzen CPUs and APUs depend on fast memory to output max performance. I ended up using this 3200 MHz kit of 2x8GB Micron DDR4 memory. I had this memory on hand from a previous project, and again, even though it is rated for 3200 MHz, it was defaulted to 2400 MHz with this system. For storage, I went with a 1TB NVMe drive from Corsair. This is the Corsair MP400, a budget-friendly NVMe drive that performs amazingly. I definitely could have got away with a smaller SSD, but I decided why not and went for the 1TB model. For wireless connectivity, I used an HP branded wireless card along with two little antennas that look like this. For the display, this is a 16x10 1080p display with a 60Hz refresh rate and a multi-touch digitizer. I am very happy I went for a touchscreen as it makes using the system much easier and never requires me to plug in a keyboard or mouse. I don't have an audio output right now, but I have both compatible speakers and a headphone board that I'll utilize in the future. Well, again, battery power isn't working just yet. It's 52 watt hours and should last for between 1 and 2 hours of gaming. All in all, the system came in a fair bit larger than I originally intended, but it's not egregiously large, and here's a size comparison next to a 15-inch laptop. So now let's talk about performance. If you've seen first-gen mobile Ryzen APU performance, you know this isn't going to be amazing, but the reality is it can play most any game you throw at it depending on the settings. I tested some of my favorite games, which most were titles not available on any mobile platform like the Switch. I tested them at 720p low, which actually looked okay because it's only a 9-inch screen. First is Fallout 4. This game at 720p low stayed in the upper 40s and even into the 50s when just casually walking around, but during intense combat the frame rate stayed in the mid 30s, but I never saw it drop below 30 at any point during my testing. Next up is GTA 5. Using the built-in benchmark at 720p low, the system actually put out an average of over 50 FPS, but in-game during intense action, the frame rate stayed in the mid to low 40s. Next up is Apex Legends, which I honestly had no idea how this was going to perform. Again, tested at 720p low and surprisingly saw the frame rates again stay in the mid 40s, which was a pretty smooth experience. With this being said, I don't think it's very smart to play competitive FPS games on a controller or with these kinds of frame rates, but to each their own. For Doom Eternal, I tested at 720p low and in-game saw the frame rate stay in the upper 30s during intense combat. Finally, for Borderlands 3, I tested at 720p low, but dropped the render resolution scaling slightly and saw an average in the mid 40s, which was a pretty enjoyable experience. Overall, performance on the system is decent and it can play pretty much any game at 720p with a console like 30 FPS or higher. These were the games I was most interested in seeing on this system, but if you have a particular one in mind, let me know what they are in the comment section below and I might test them in the next video. This project is definitely bigger and rougher around the edges than I would have liked, but at the end of the day, I'm just happy I was able to put something like this together. If you have recommendations for learning circuitry that would be relevant to this kind of stuff, or info on 3D modeling for enclosures for electronics, then let me know in the comments below. Also, I could have went many different directions with this project, so let me know what you would have done differently. So yeah guys, I think this wraps this video up. I hope you guys enjoyed it. If you did, make sure to give this video a big thumbs up and consider subscribing for more PC and tech related content in the future. And as always, this is Matt from Tech by Matt, signing out.